Okay, we have 5 problems left, and it looks like we have to find the area of this trapezoid. Don't forget to leave it in radical form. So once again, the formula for a trapezoid is 1/2 the height, and we've got to take base 1 and add it to base 2. So it looks like we just have to fill in 3 numbers in here. Well, as I'm analyzing this picture in here, it's not just any trapezoid. I have evidence that we have an isosceles trapezoid. What other evidence do I notice in here? Well, this is going to be a 30, 60, 90 triangle, and it's also going to be congruent to this one, and that only occurs, this congruency, when we have isosceles triangles. Also in the middle here, take notice that this little green section, this is a rectangle. So whatever this side is, for example, that's what that side is going to be. So where do we start? Well, I start by knowing that this is a 30, 60, 90 shortcut, and I know the height of the trapezoid, which is the middle side in this 30, 60, 90 shortcut. So in this case, I'm going to go backwards within this little shortcut to find the smallest side. So I'm going to take 12 and divide it by radical 3. And we've done that before. When you simplify that radical, it turns out to be 4 radical 3. Which is actually going to be the same as that side in here, because remember those 2 triangles are congruent whenever we have an isosceles triangle. And if that's 4 radical 3, we can actually deduce what the, we actually find what the hypotenuse is here. That's always going to be double. Now it turns out we don't need this side when we do our calculations in here. We're only going to focus on the bases and the height, but it doesn't hurt to help. It doesn't hurt to understand how the smallest side, the 4 radical 3, and the hypotenuse are related. So what other clue haven't we used yet? Well, we haven't used this clue in here that says AD is going to be 18 radical 3. So far what I notice is we know some of the base and some of the other base in here. That's 8 radical 3. Well, if all together I have 18 radical 3, and I already know this part is 8 radical 3, I must know that that is 10 radical 3, which means that the top base has to be 10 radical 3. Let's make that a little nicer in here. So it's going to be 10 radical 3. So I think we now have enough information to plug in all of our numbers. Well, the height in here is going to be 12. And the first base, I'll just call it the top base. That's going to be 10 radical 3. And the bottom base is all these added together, or otherwise known as 18 radical 3. So when we're simplifying radicals, notice both of those have a radical in them. That's great news. So half of 12 is going to be 6, and altogether we have 28 radical 3. And we just have to simplify this a little further, and times 28 times 6, that's going to be 168 radical 3 units squared, and it did want us to leave it in radical form, so we're good to go. All right, let's take a look at the next one. Well, here we have an inscribed equilateral triangle, and we have a circumscribed circle. So in this case, we're just trying to find the area of the yellow region, and unfortunately we don't have a formula for that yellow region. What we do know is if we can brainstorm to realize that the yellow area is really made up of taking the whole entire circle. If we imagine that we wanted the whole entire area of the circle, and then we're going to subtract out the area of the equilateral triangle, what's left is our yellow shaded region. So in this case, let's write the formulas we need. We need pi r squared for the circle. And I like my shortcut formula for the equilateral triangle. That's side squared radical 3 over 4. So we really just need 2 variables. We have to know what the r is. And that's good news. We know what that is. That's 12. So 12 squared is 144 pi. And the side of the square is just going to be a little more challenging to find. What we do have to recognize in a 30, it's going to be an equilateral triangle here, is if I draw this line in, which turns out to be the apothem, and also a really nice side to make this nice right triangle in here. It's not just any right triangle. If you notice, this dashed 12 bisects the 60, so we create a 30, 60, 90 triangle. What I'm really interested in is not that letter A. I'm really interested in this little baby x side in here, which is going to be half of one side. So if I use the shortcuts in here, if the hypotenuse is 12, this side is the smallest side. That's always going to be half of the hypotenuse. And then I always take the smallest side and I times it by radical 3, and that's going to be the side opposite the 60 degrees. So in that case, if that's 6 radical 3, this portion 6 radical 3, the entire length of one side is going to be 12 radical 3. So in this case, let's just plug it in. We have 12 radical 3 squared times radical 3 divided by 4. So what we want to do is leave this in pi radical form. How do we do that? Well, here's a pi. And over here, I'm going to take 12 radical 3, and I'm going to square it. So when we square 12, we get 144. And when we square radical 3, we get 3. So 144 times 3 is 432 radical 3 divided by 4. Well, the only thing left to kind of think about is what can we do to simplify 432 divided by 4? Well, that turns out to be a nice number. So that's going to be 144 pi minus 108 radical 3. And that is our answer in pi radical form. Very sophisticated answer. Don't be uncomfortable when we see answers like that. It's going to be very common as you get a little more sophisticated in your little math careers here. That is a very acceptable answer in pi radical form. It actually takes longer to put in a decimal form if you think about it. We've got to start breaking our calculator out and punching numbers in, and it's just not as considered as beautiful as something as simple as 144 pi minus 108 radical 3. Now let's do another one. We got number 18 here. This is unusual. It looks like we have a rectangle and a bunch of circles, and the area that we want to find is just the blue regions. Okay, let me use blue. We would just want to find the blue regions in pi radical form. So the only dimension we're given here is 8, and 8 looks like one side of the rectangle. I kind of wish I knew the other end of the rectangle, but what you got to see here is a very subtle clue that if that's 8, that would be 8, that would be 8, that would be 8. And notice if I draw it this way, maybe it's a little easier to see. It looks like the diameter is also 8. So if I drew it another way, that would be 8, that would be 8, and that would be 8, which gives birth to being the bottom dimension, or the top dimension of the rectangle is 24. So we just went on a hunt there for the other little side and forgot the bigger picture. We want to find the area of the blue region, and let's really map out that strategy. Well, similar to the previous problem, we're going to take the area of the larger shape, in this case the rectangle, and we're going to subtract out 3 circles. That kind of represents a circle. And these are all congruent circles in here. It tells us that right from the beginning. So what I want to do here is area of the rectangle minus the 3 circles, and that's going to be the remaining leftover area, which is all blue stuff. So what is the rectangle? Well, we know these dimensions. It's 8 times 24. Well, 8 times 24 looks like it's going to be 192. And over here, it looks like we just need to know 3 times pi r squared. Well, what is r? R is not 8. Remember, this whole entire length is 8. So it looks like the radius would be 4. So 4 squared is 16. 16 times 3 is 48. So how do I write my number all fancy? It's 192 and 48 pi. And that's it. We can't combine pi's into just a regular number like 192. So that's the answer to this shaded blue region in here, 192 minus 48 pi. Let's do 2 more in here. This is a beautiful picture where we have a larger circle and then 2 smaller congruent circles, and we're going to try to find the area of the green and blue regions in here. And the only clue they tell us is the diameter of the larger circle is 64. So let's just draw that in. Well, if that's 64, hopefully you can recognize right away that this would be 32, and that would be 32. Well, why would I make mention to that? It's because if we just know this part is 32, then we would know that the radius is 16 to each of these smaller circles. So what did I just realize? The radius of the bigger circle turns out to be 32, and the radius of the smaller circle turns out to be 16. So why do we need these radii in here? Because we want to find this shaded region. Which one do I want to find first? Well, before we make a strategy or anything, I want you to make mention that if the blue is the color representing the circle on the bottom, blue should be the circle representing the one on top because they're the same exact area. And the symmetry in here, once again, if we're going to use green for the region on the right, well, the region on the left is going to be exactly the same. So now we just have really just two different types of colors in here, the blue team versus the green team. And if I isolate, how would I discover the blue regions, the green regions, for example? I would take the largest circle, and I'm going to subtract off the two little circles. Because if I take the entire large circle right here, and I subtract off the two little circles, then what's left is going to be the green area. Because the whole circle is not green, just the sections less the two shaded blue regions. So in this case, I'm going to go pi r squared. Well, the radius of the larger circle is 32, so that's going to be 32 squared. And then the radius of the smaller circle is going to be 16. So I got 2, because there's 2 of those circles, times pi times 16 squared. Warning, 16 squared is not 32. So let's multiply all this out. The one on the left is 32 times 32, 32 squared. That's 1024 pi. And then on the region on the right, that's 16 squared. I think that's 256 times 2. That's going to be 512 pi. Well, since both of these are pi, 1024 minus 512, notice that's 512. And what does that represent now? That represents all of the green region, because that's the big circle minus the two little circles. But remember the original problem. We didn't want all the green. We just wanted half the green. So what would I do to that number? Well, let's divide it by 2. And if I divide it by 2, I take 512 divided by 2. That turns out to be 256 pi. That is the area just of the green region. Another part of this problem said not only find the green and the blue regions in here. Notice it says find the green region and find the blue regions. It also says, hey, what do you notice when you compare these two regions in here? So let's just find the area of the blue circle and one blue circle and compare. Because remember, that was part of the original problem. Just find the blue and the green area and compare them. Well, remember, that's going to be pi 16 squared, because that's the radius of the smaller circle. And what do you know? It looks like the area of the blue region, which is just one circle, is the same exact number. And that's what we wanted to realize here, is they're the same. Well, why is this picture then so beautiful? Is because each of these regions in here are exactly the same. We knew the two green regions were the same. We knew the two circles were the same. And this is kind of hard to visualize right now, but each of these 4 regions in here, they all have the same exact area. So think about taking a circle and kind of twisting and turning it and morphing it into something different. You would get the area of the green region, and the same is true thinking backwards. If you took the area of the green region, you kind of morphed it into an exact circle, you would get that entire blue circle. So we have one more problem in here, number 20. What does 20 look like? Well, we want to find the total area of just the green shaded regions, not the blue one here. So keep in mind, we don't want the blue. We just want the blue. We want the green ones. But the blue one's important to think about because there's a beautiful symmetry of all 4 of these regions combined is everything except for the circle, in the context of if we took the area of the square, and that is a square, and we subtracted out the entire circle, that would give us all of the shaded regions. But what we want to do to that number, because that's kind of too much, that would be 3 green and 1 blue. What we want to do is times this number by 3/4 because we want 3/4 of the shaded region. So in this case, we want to find the perimeter, and the perimeter of the square is 288. Well, 288 divided by 4, because all sides in a square are congruent, that would be 72. All those sides are 72. Well, what do you want to come away with if that's 72? One full side is draw the radius in, and it turns out the radius would be half of that number. That would be 36. Now we have enough information to find the the area of the square, which is side squared. Warning, it's not 72 times 2. It's 72 squared, which is 5,184. And on this side, we want to go to pi 36 squared. Again, 36 times 2 is not 36 squared. 36 squared is a total of 1296 pi. And so remember, don't forget that what we just found here is all of the shaded regions. We don't want all of them. We want the ones that are just green. So in this case, since we want 3 out of the 4 regions, we are going to times it by 3/4. So I take each of these numbers in here, and I'm going to distribute the number 3/4. So I'm going to take 5184, times it by 3, divided by 4. Lucky for us, that turns into a whole number. That is 3,888. The same thing over here. This is going to be a nice number. 1296 times 3 divided by 4 is 972 pi. So it wanted us to leave our answer in pi form, and there we go. That's our pi form. It's nice to leave units squared, and that's it. That's number 20. A lot of thinking going on in all these problems. We got shortcuts, we got trig, we got Pythagoras, we got radicals, we got pi radical form, we got some strategies in here. So hopefully this has been helpful, and talk to you soon.